In the previous lecture, we had gone through the application of two of the duct design methods, that is the velocity method and the equal friction method. And I had also mentioned to you that there is a third method which is known as the static regain method, and it is an iterative procedure, so it is more suitable for application using computers. However, I will give you a basic idea of that iterative procedure by applying it to a very small section of a duct layout, a very simple layout, and then we will proceed onwards. The static regain method is commonly used for high velocity systems with long duct runs, especially in large systems, and because you will see that it involves a gradual reduction in the velocity as we move from one section of the layout to another. So that's why it is more suitable for high velocity systems, because you start with low velocity systems, then you will end up with very low velocities later on in the duct layout, which will not be practical for our requirements. So that is why it is commonly used for high velocity systems. Another restriction is that it is used for designing supply duct networks and not for return duct layouts. Whatever you do is that the first thing is the selection of the velocity leaving the main duct after the fan. So that velocity has to be selected, and once we have done that, then as we move in each of the runs, as I mentioned earlier, that velocities are reduced in such a manner that when you reduce the velocity, there is an increase in the static pressure, and that increase in the static pressure should be the same as the pressure drop in that particular section of the run. That is, the rise in the static pressure should balance the pressure drop, and we will look at it schematically as well, and then I'll try to put some numbers to make sense of what is shown in the schematic diagram. So we have a very simple case. You can see we have a duct, and we have from the duct there is a branch takeoff at one point over here, then there is another branch takeoff at this point over here, and you know that the total pressure in any fluid that is flowing is the sum of the static and dynamic pressures. So if we decrease the velocity, that means the dynamic pressure will reduce and consequently the static pressure will increase. Let's say at section 1 the static pressure is 50 pascals and we have a velocity of 8 meters per second, which will be equal to 38.4 pascals using a standard density of air of 1.2 kilograms per meter cube. Now if I move from section 1 to section 2 and I reduce the velocity from 8 meters per second to 7 meters per second, it will mean that the dynamic pressure becomes 29.4 pascals, and there is a difference of 9 pascals between the dynamic pressure that we had at section 1 and the dynamic pressure we have at section 2. That means as soon as we move from section 1 into this small part of the duct with a smaller area where we have the takeoff, and we have increased the velocity over here from decreased the velocity from 8 meters per second to 7 meters per second, that means it will lead to a rise in the static pressure, and the static pressure will now become 59 pascals. And what we are saying is that this velocity that we have chosen as 7 meters per second is such that this increase in the static pressure balances the frictional and dynamic pressure loss between this section 1 and section 2. So if there is a pressure drop over here, call it delta P over here. I'll just call it delta P, and that is equal to 9 pascals. So what will happen as a result of this? We have a static pressure which increases from 50 to, we'll say P static is equal to 59 pascals. So there is an increase in the static pressure due to the reduction in the velocity. And then we had, at this point, we had a static pressure of 50 pascals. 50 pascals, and the velocity was 8 meters per second. So that was the condition just before the branch takeoff at section 1. And as soon as you move into this region where we have reduced the velocity, the static pressure becomes 59 pascals when the velocity becomes equal to 7 meters per second. I'll just move the numbers a little so we have more space. That is when we reach section 2. There will be a decrease in the pressure due to the frictional pressure drop and any minor losses or dynamic losses during this section of the duct layout or the run, and then we will again end up with a pressure of static pressure of 50 pascals. And that is what we are saying, that PS1 will become equal to PS2 over here. So reduction in the velocity causes an increase in the static pressure of 9 pascals, and then again there is a pressure drop of 9 pascals, giving us the value of 50 pascals. That was what we started with. And because the frictional pressure drop and the dynamic losses are dependent on the velocity itself, we cannot predict just in one step what reduction in the velocity will give you a certain pressure drop and an equal rise in the static pressure. It has to be a trial and error solution. And when we solve a example, then you will see how that trial and error solution is carried out. Okay. So the basic idea is to successively reduce the velocity such that the increase in static pressure balances the incoming pressure drop, both frictional and dynamic. And this is shown by this equation over here. But there is another factor, you can see R over here. I'll come to that. Consider for the moment that this R is not present over here. I'll just block it out. Let's say I'll just block it out. So it's not over here. So the change in the dynamic pressure because we had a higher velocity at section 1, a lower at 2. So this is the change in the dynamic pressure or a decrease in the dynamic pressure, and that decrease in the dynamic pressure will be equal to the increase in the static pressure under ideal conditions. As we had looked at those values above, that decreasing the velocity from 8 to 7 meters per second caused a change of 9 pascals in the dynamic pressure, and that means the static pressure rose by 9 pascals. And what we said, that that increase in the static pressure should be equal to the pressure drop in the duct run that we are working with. So that is shown on the left hand side. Delta Pf2 and delta Pd2 are the frictional and dynamic losses, pressure losses. Then we come to this factor R. Under ideal conditions, all of the change in the dynamic pressure is converted into a increase in the static pressure. But actually what happens, that there are losses. So not all of the dynamic pressure reduction is converted into a static pressure rise, and that is shown by this factor R, which is known as the static regain factor. For example, if 90% of the static pressure reduction is converted into a 90% of the dynamic pressure reduction is converted into a static pressure rise, R will have a value of 0.9. That means 10% are the losses, and that static regain factor, when we work with the numerical, we will be given this value for a particular problem. So that is the critical part of this method, that is the static regain method. And then once we have obtained the desired velocity for a particular segment of the layout by using the trial and error solution, we move forward to the next run. We will again reduce the velocity and repeat the process of iteration, and that is described in the slides that you are looking at. That initially we have the flow rate and the velocity, so we will find out the duct dimensions from that information. Then we moved on to the next section. In the next section we will assume a velocity, go through a trial and error solution, and when the solution converges, we move on to the next section and repeat the process. So the advantages of the static regain method is that it gives us a more balanced design, and unnecessary damping is reduced. And as I had said earlier at the beginning, that because we are successively reducing the velocities, the duct size may increase in the airflow direction, because at some point we might have a large pressure drop if we do not increase the duct size. So that could be a possibility. And I will now look at the application of this method to a part of a very simple duct layout. So we will move on to the example problem next. So we have a simple duct system with 3 diffusers, each having a flow rate of 1 cubic meters per second, and you are shown where the fan planum is. We are given the static regain factor, and because we need the starting velocity after the fan planum, which is given to us as 8.5 meters per second, and we are also given the various loss coefficients, one at entrance, then the T through at B, so that means we are moving in this direction, then the T through at C, and this 90-degree elbow. So we will apply the static regain method only to this main duct section, that is A to B, B to C, and then C to D. So that is all that we will do in this numerical. We have to size these 3 segments by using the static regain method. Sizing segment A to B, we do not need the static regain method because we will have the total volume flow rate. We are given the velocity of 8.5 meters per second, so you can easily find out the cross-sectional area. Assuming it's a circular duct, you will then find out the duct diameter, and then we move on to segment BC and apply the static regain methods. That is where we will see the application of this method. Using the information given, we know that the total volume flow rate will be the sum of the volume flow rates from the three diffusers, which is 3 cubic meters per second. The velocity is given as 8.5 meters per second, so we find out the cross-sectional area of segment AB and then the diameter of segment AB, which is 670 millimeters. Next is the part of the duct shown by segment BC. Because we have already taken 1 cubic meter per second at this T junction into the diffuser from B, so the flow rate in the segment BC is 2 cubic meters per second. The static regain factor is given, and in this segment we just have one source of minor loss, that is the T, and we are moving through the T, so the loss coefficient for T through is 0.35, and we will calculate the static regain. That means how much is the increase in the static pressure due to the reduction in the velocity. So the velocity, remember, will be lower in segment BC as compared to the velocity in segment AB. So you will have the difference of the velocities squared into the density by 2, that is half rho v square, and then we will multiply it by the static regain factor. So this is the decrease in the dynamic pressure when we move from segment AB to segment BC. The velocity in segment AB is given as 8.5, but the velocity in segment BC is not known to us. That is what we have to guess, and we have to guess it such that the increase in the static pressure will be the same as the pressure drop that we will obtain in segment BC. So the only one unknown was the velocity in segment BC. The rest of the values are given to us, and we get the equation which we have numbered as equation 1. The other thing is now is to look at the pressure drop in this segment BC, which will be the sum of the frictional pressure drop and the pressure drop due to dynamic losses. Okay. The duct lengths I have not shown over here, but this is actually 10 meters, so I'll just write it down over here. This is 10 meters, and the other one will be 20 meters, and this one over here is also 10 meters. Yes. So those are given to us in the problem, and as we had done earlier, the frictional pressure drop is the product of the pressure gradient, pressure drop per unit length, multiplied by the length of the duct, and the minor losses are, or the dynamic losses are, half rho v square into the loss coefficient. We again substitute the various values that are known to us, and we get equation 2. Now if you look at equation 2, again it has the same unknown, that is the velocity in segment BC, and even this pressure drop delta P by L will depend on the velocity in that segment, which is unknown. So that is why we need an iterative method or a trial and error solution, and I will now move on to that solution. You can see that I have guessed a value of 7 meters per second in duct segment BC, and we know the volume flow rate in that segment, that is 2 cubic meters per second. Against those two values, that is the volume flow rate and the velocity, we will go to the friction chart and find out the value of delta P by L. Now, because we now know the value of delta P by L and we have a guess value of the velocity, we will substitute those two values in equations 1 and 2. If our guess was good enough, then both the equations would give us almost the same values. But you can see that the static regain value from equation 1 is 10.46, whereas the value of the pressure drop in that segment comes out to be 18.19 pascals. So there is a considerable difference between the two, and we want to reduce this difference between the two values by making another guess about the velocity. So what I want to do is to increase the value of delta P static regain. And if we look at it in this equation 1, if I want to increase the value of delta P, I need to reduce the velocity VBC. So you can see I have the next guess as 6.5 meters per second. Against that, I will find out again. You can see now, because both delta P by L is also dependent on the velocity, this value will change. So both the velocity and delta P by L values have changed. As a result, we again have different values of the static regain and the pressure drop, and they are now closer. However, the value of the static regain is still on the lower side, and we can further reduce the velocity. So we make a third guess of 6.25, and this time you can see that the static regain value becomes slightly higher than the delta P value for the duct run. So that is, we can fine tune our result by slightly again increasing. We want to now reduce this value of 14.93, so we will slightly increase the value VBC, and I've just made it 6.3, and at this value you can see that the two values, that is the static regain value and the pressure drop, both, which is the sum of both frictional and dynamic losses, they are quite close together, and we can stop our iteration at this point, and we can say now that the velocity that we have guessed to be 6.3 meters per second is the velocity at which the static regain will balance the pressure drop, and this is the value that we can then use to find out the cross-sectional area. Again, divide the volume flow rate by the velocity and then convert this into the corresponding diameter of that segment, that is segment BC, and you get a duct diameter of 636 mm. I will show you these values that we have, that we started with a guess of 7 meters, then we went to 6.5 meters, 6.25 and 6.3, and for each we had to find out delta P by L from the friction chart. The volume flow rate remains unchanged, that was 2000 liters per second, and I've already marked these values over here. So you can see at 2000 liters per second and at 7 meters per second, the intersection of these two lines will provide us with the value of the friction factor from the friction chart, and this is just under 0.8, so I've used a value of 0.79. The next guess was 6.5, so you can see that if we will have to draw a line ourselves which has a value of 6.5, so I'll try to just place it some in the center. So we are roughly in the center between 6 and 7, and then again what you will have to do, where it intersects this line of 2000 liters per second, you will read the value of the friction factor. So if you read the value of the friction factor, over here, I'll see, we can see it is, this is 0.65, around 6.65, and I think that is what we had, 0.67. so this is the value that you will read from the chart, because I've drawn it just approximately. When you use a proper scale to read the values, the value will be around 0.67 or so. And then again you will have to make another guess for VBC, which will now be 6.25. we again change this line and we will have another point of intersection, which is, again you can see this is 0.5, this is close to 0.6. Let me see what we had over here. Yes, we had 0.6 over here, and then after fine-tuning you just shift this line slightly upwards, and when you do so slightly upwards, you will get a value of around 0.61. so that is how we found out the dimensions of the segment BC, and the same will be done for the remaining segment, that is CD. And in segment CD we will have a starting, because we now have a initial velocity of 6.3, our next guess of the velocity will be less than this value of 6.3, and I will move on to that part of the solution. And you can see that this time the velocity volume flow rate is further reduced, because there was another T from another 1 cubic meter per second went into another second diffuser, and so we have a volume flow rate of 1 cubic meter per second. Then we had two sources of minor losses, that is again T through, and then we have had a 90-degree bend also. Static regain factor remains unchanged, it is 0.75. we again write the equations for the static regain and the pressure drop, and this time the velocity, initial velocity was VBC, and the guess velocity will be VCD. We substitute the known values, we get equation 3. Then again we had the duct length of 20 meters, and then delta P by L is unknown. This KL values are known. We know the density, the standard density is 1.2 kilograms per meter cube, and that will give us equation 4, in which only VCD and delta P by L are unknown. And you can see again the trial and error method I have gone through. I started with a velocity of 5 meters per second, found out the frictional pressure drop per unit length, found out the value of static regain and the corresponding pressure drop. There's a very significant difference between the two values. One is very high, this one is very small comparatively, so I need to increase the value of the static regain. That means I have to reduce the velocity appreciably, and I reduced it to 4 meters per second. When I reduced it to 4 meters per second, the two values are close enough, and I can just reduce the value slightly, because I still want to increase the value of static regain, but by a small amount. So I made my next guess as 3.9 meters per second, at which the static regain is 11.02 pascals, whereas the pressure drop is 11.26 pascals, and that is where we can stop the iteration and take the value 3.9 meters per second as the velocity in segment CD. And again, by using the volume flow rate in segment CD, we find out the cross-sectional area and the duct diameter, which is 571 millimeter. So you can see, if it had been a large layout with tens of runs and takeoffs, etc., doing this duct design by using the static regain method manually would have been a very tedious job. That's why it is much more suitable for computer-based solutions. And that is all for this lecture. we will continue with a new topic in the next lecture.